Welcome to EDU World Space.
Hello. So in this problem, we're dealing with a boat. We'll label it mass little m. So mass m little b. And then we have a man and a woman standing at the end of the boat. And then what's going to happen is that each of our people, the man and the woman, are going to sequentially jump off the boat with a velocity completely to the right at 16 meters per second. Now that's relative, relative to the boat. So we have to keep that in mind. The speeds given are given relative to the boat. And I believe the mass of the boat is 300 pounds. Let me write these zeros better. 300 pounds. The mass of the man is 180 pounds. And the mass of the woman is 120 pounds. So those are the things we need to know. The question we want to answer is how much work is done by each person as they jump off the boat. Now, remember, if we want to know how much work is done on a system, we need to know the change in the kinetic energy of that system. So what is the kinetic energy difference, right, between some final state and some initial state of our system? Now, remember, we have to figure out the work done by each person, the man and the woman, as they each jump off the boat. So, what's going to happen, right, is to figure out the work done by the woman as she jumps off the boat, is we need to figure out the kinetic energy of our system after the woman has jumped off the boat, compare it to the kinetic energy of our system before the woman has jumped off the boat. Well, in order to figure out the kinetic energy of our system after the woman's jumped off the boat, we're going to need to figure out both how fast the woman is traveling to the right, which we're given, so that's nice. And then we have to figure out how fast is the boat and the man traveling to the left after the woman jumps off, right? Because this is actually modeled as sort of an explosion, right? We have something sitting at rest, sitting here, which actually means our initial kinetic energy will be zero for figuring out the work done by the woman as she jumps off. Right? It's kind of like a little explosion. So nothing is moving, the woman's going to jump out to the right, and therefore everything has to recoil to the left. Now we can figure out, right, how fast the boat and man combination is going to be going. How fast are they going to go? From conservation of momentum, right? So we know initially when both of these are not, when everything is not moving, right, we do a little momentum conservation analysis real quick. We see that initially there is no momentum, right? So initially we have zero momentum before the woman jumps off the boat. And then afterward, we're going to have the boat heading backward. The boat plus the man, right? The man is still on the boat, he hasn't jumped yet, moving back at some velocity, which I'll label it b plus m. So that's the velocity of the boat plus the man. Right, so they're going to be heading back together at some speed while the woman heads off to the right at the velocity of 16 meters a second relative to the velocity of the boat itself, right? So this velocity we're given, the 16 meters a second, is given relative to the boat. So we have to take into account the fact that we have to adjust and move really to a frame that's moving along with the boat, or adjust the speed 16 so that she's actually traveling a little bit less fast in a rest frame observing the boat move. Now, right, what do we want to do? We want to solve for this velocity of the boat and man together because we need to know that to figure out the total kinetic energy of the system after the woman has jumped off the boat. So doing some quick algebra here, we see that the velocity of the boat plus the man together is given by the mass of the... Here, let me rewrite this a little bit. My tablet's messing up a tad. So, the velocity of the boat plus man moving together is going to end up being, by doing some algebra, the mass of the woman multiplied by the velocity that she jumps out, the 16 meters a second, divided by what ends up being the total mass of the system, which is the mass of the boat plus the mass of the man plus the mass of the woman. We know all these values. We don't have to convert the pounds to slugs because we know that the units are going to cancel. So we just plug everything in that we have it, and we end up seeing that the boat and man actually travel backward after the woman jumps off at 3.2 feet per sorry, the tablet's messing up a little bit, feet per second. Okay, well, now that we know how fast the man and the boat are traveling back after the woman jumps off, we can figure out the total kinetic energy after the woman has jumped off, right? So let's go back and figure out what the work done by the woman is going to be as she jumps. So the work done by the woman is equal to, right, the change in kinetic energy of our system. So after the woman jumps off the boat, remember that the boat and man have kinetic energy, so they travel to the left at 3.2 meters a second, and we can express the combined kinetic energy of the man and the boat as given by this, viewed from a rest frame. Then we also have the kinetic energy of the woman, and remember, she has jumped at 16 meters a second, which is the V we have, but relative to the boat. So if we're calculating her kinetic energy from a rest frame, we have to subtract out that velocity we found that the boat was traveling after the woman jumps off. Right, and so now this is the total, this is just TF, that is the total kinetic energy after the woman has jumped off, because she's heading to the right at 16 meters a second relative to the boat, and then the boat and the man are heading back to the left. And then initially, what is the kinetic energy we have? Well, the man, the woman, and the boat are all at rest, and are a rest frame, so therefore there is no kinetic energy there. Now, when I solve all this out, let me plug everything in real quick, just to show you what we need to do. Right, we have 1/2 plus the weight of the boat, which is 300 pounds, plus the weight of the man, which is 180 pounds. Now remember, the pounds is a measure of force, not mass. And when we have an m in our equation, that means mass. So we need to use a conversion of 32.174 pounds per slug, right, which is the unit we need when we're doing feet second, using feet per second as our velocities. I think this is actually, I'm sorry, this isn't not a meters per second. This is a feet per second. Oops. So 16 feet per second. Okay, so we know we're moving 3.2 feet per second for the boat and the man. And then, of course, we add the kinetic energy of the woman. She's 120 pounds. She's jumped to 16. Jumped 16 feet per second, but that's relative to the boat that's moving at 3.2 feet per second. We square all that, and of course, we subtract out our 0. And before we're done, remember to convert our force of 120 pounds to, write that 3 better, 32.174 point, and that's pounds per slug. Okay, put all this into our calculator, and what we see is that the work done by the woman as she jumps off is going to be able to change in kinetic energy from before she jumped off and after, and that ends up being 382 feet pounds, right, which is a distance times a force, and that is units of energy, right? So we have 382 feet pounds of work are done on the are done by the woman as she jumps. Cool. Now, in order to figure out how much kinetic energy is or how much energy or work is done by the man as he jumps off. We just need to redo this process, but considering a system where the woman has already jumped off and the man needs to jump off now. So first we need to figure out, well, how fast is the boat going to be traveling after the man jumps off? So why don't we load up a new page here and figure that out? Well, we can do that through another momentum calculation, right? So another momentum conservation calculation. Now, this is going to be the point initially where the boat is heading back and to the left, right? So the woman has jumped off the boat in this case, and so it's the man in the boat heading back at the velocity of the boat plus the man. And then afterward, after the man jumps off the boat, remember the woman has already jumped off the boat, we are going to have the man jumping off and heading to the right at a velocity of 16 feet per second, but that again is relative to the velocity of the boat after the man jumps off. And then the boat is going to continue to head backward at some new speed we want to calculate, right? The velocity of the boat. And remember, again, the 16 feet per second is always relative to the velocity of the boat, so we have to shift it in this calculation here. Right, we move some things around, solve for the velocity of the boat here, right? We want to solve for this, so we got to group them together and solve for that. And we end up getting that the velocity of the boat heading back is equal to the mass of the man times v plus the combined mass of the boat and the man times the combined velocity of the boat and the man, all divided by the total mass of our system. And this ends up being 9.2 feet per second. So right, that's this situation. We're comparing the two situations where we initially have, boat's not the best, the man standing on the side of the boat here, and then we're going to move to a system where this is the boat. And right, it was headed back this way, or back completely to the left. Let me draw that again. Oops. Okay, here we go. At a velocity of the v plus m. And then we're going to, as our initial state, and we've moved to a final state of, now we have the boat heading back at 9.2 feet per second in the rest frame, and the man is actually jumping this way at a velocity of, let's see, 16 minus 9.2. So what is that? Let's see, 5 or 6.8, right? 6.8 feet per second. Yeah. Okay, now that we know how fast the boat is going backward, we just got to do our calculation again. So to figure out how much work is done by the man as they jump off the boat, we figure out what's the final kinetic energy after the man has jumped off the boat and compare that to the initial kinetic energy before the man jumps off the boat. So after the man jumps off the boat, right, we have the 1/2 m b squared, then, sorry, 1/2 mass of the boat times the velocity of the boat squared, so we have the kinetic energy of the boat, plus 1/2 the mass of the man times the velocity of the man squared, but again, that's velocity in our rest frame, so we must shift it, that's 16 feet per second, by the velocity of the boat. This will end up being our 6.8 feet per second. Now, let's compare this to the initial kinetic energy of the system, which is not 0 this time, because the boat, remember, is heading back at a velocity of what I think it was 3.2 meters per second, right? So we have 1/2, before the man jumps off, we have a kinetic energy of 1/2 of the mass combined, the boat and the man, those masses combined, multiplied by the velocity of the boat plus the man, all squared. So we know everything here, and that is going to be our answer. We should need to plug everything in here. Remember, when we plug in our weights here to convert by the 3.2174 pounds per slug, same thing here, right? And here. So remember to convert before you do all that stuff. So plug all this stuff in, and we end up getting an answer of 447 Again, feet, pounds, distance times a force, and that gives us a work. So by comparing the change in kinetic energy of a system, we can figure out how much work is done in the process between these two states, in this case by either the man or the woman. And sometimes we needed to do a little bit of momentum analysis, conservation of momentum, in order to figure out what the velocities of our different masses were, in order to figure out their individual kinetic energies, in order to then figure out the difference in the kinetic energies between two states. So that's how we ended up solving this problem.